Hey guys, I'm starting a new project today, and I'm gonna record most of it. And so this is gonna be a long one. Well, let me explain. So it all started with my previous video. By the way, I noticed I say a lot, so I'm gonna work on that, and maybe on some next video we're gonna code something. So every time I say there's like a pop-up on the screen, so I stop saying it. But so one of my first video on YouTube was AI girlfriend versus dogs, I think, or something along those lines. And a big inspiration for that video was see, that's the again, AI girlfriend versus AI pets. If you haven't watched that, I'm gonna link it somewhere. But a big inspiration of this video was the cool Disney robot. So this bipedal robotic character. Let's see if I can find the paper. Disney, that's the paper. And that is not the paper. This is the paper. Anyways, I showed it to a friend. I think every like tech person, engineer has seen this, and again, it's pretty cool. The coolest takeaway from this for us was that yeah, sure, like we all knew you could build a computer to control a robot, a bipedal, keep its balance and so on. But what's so cool about this one is that it does it following animations, right? So it does it with style. If you haven't seen it, it kind of has a quirky walk and all these emotes that makes it feel very quote unquote human. And so we're gonna replicate this paper. Now we're not gonna replicate it as what it is, as like the shape of the robot. And the reason why is because like we wanted something more stable. So the original idea was to build this thing and send it to the Antarctic, because basically, yeah, in a perfect world we'll send it to Mars, like kind of like a Curiosity rovers for Mars, and we'll stream it and we'll get a ton of views. But we cannot send it to Mars right now, so Antarctic is as kind of close enough. But anyways, we're not gonna do that for B1. B1, we're calling it Antarctic, keeping the name Antarctic. B1 build. It's gonna be a robot dog. And then the reason why we went with dog, the quadrupeds, like four-legged robots, like the Boston Dynamics quad. It's because there's a bunch of open source platforms already built for us, which we can build upon, and also the kinematics of these shape form factor are very easy to model, well understood from a CADing perspective. When we're building it and stuff like that, there's plenty of actuators that will do just fine for these. And then from a modeling and model training point of view, there's a ton of papers that we can closely follow. So I have a Notion here where I keep updates and stuff like that. I only started working on it this recently, August 25th. Today is September 6th. Today's the second day that I work on these. And so I'll show you where I'm at, and then I'm gonna just work on this stuff for the next hour or so. I don't know if you're gonna find these fun. I find it fun when I see other people doing work that I find interesting. So I'm just putting this content out there, see if anyone else who's into robotics will find it fun. I'm gonna build a robot dog from scratch, close from scratch, that walks funny, and we're gonna teach it how to walk funny and also how to dig holes. So I live in California, we have beaches all over. We're gonna dig a hole on the beach. So the purpose of this robot is gonna be to walk with charisma and dig holes. That's what we're building today. Yeah. And then we have some constraints here. We've set, basically, when you first start building a platform, you want to set some constraints. Constraints are important in engineering, so that's how things can start shaping up. So we have some maximum dimensions. This is entirely based on our 3D printer size. So I actually bought a 3D printer, different video, you can watch it. It's a Bamboo P1S. It's really cool. So as part of this series, I'm probably also going to include some shots of that. So we have some overall dimensions. We have a budget of $1,000 to build. It's probably going to be closer to $2,000 at the end of that. And not starting from entirely from scratch. We're actually starting from the Stingo quadruped platform, open source. It's on GitHub here, and it's also on GrabCAD. If you don't know GrabCAD is basically, if GitHub is for code, GrabCAD is for 3D CAD. And so this is what they built, and I personally think this looks ugly. It looks, very chunky. It doesn't look nimble. Doesn't look elegant. I like to build things that look elegant. It costs the same thing to make, a piece of metal that's ugly versus a piece of metal that's nice. So we're gonna make it look nice, but we're gonna like use a lot of their stuff. One of the issues with open source hardware, of course, is that you don't know where they source all the components. Some stuff it's out of stock now. It's like some server from China. They don't stop making it and stuff like that. And then the other thing is like my experience with open source hardware. Let me pull a prop for these. I recently built some robotic grappers. These are meant for teleoperated robot arms. And this was also an open source design. It came out pretty nice. But the thing with hardware is, if you don't know much about hardware, you see this and it looks fine. But there's all kinds of little fits and all kinds of little details that are actually not fully fleshed out. For example, here you can see a screw that is not actually flush. Here you can see that we're missing a screw here because whomever designed this 3D part didn't make the hole tight enough for a metal insert to be inserted there. So whenever you're basically borrowing from an open source hardware project or want to build an open source hardware project, you have to take a close look at like how things work. Similar to software, of course, if software, you're borrowing open source software, it doesn't run, you can kind of figure it out. With hardware, you might send out parts to manufacturer. It might be like 2-3 weeks later, you might be like a few $100s in the hole before you realize something super simple that it's like, oh, someone made this hole like 0.1 millimeters too big and now this doesn't fit. And so with this Dingo platform, there's all kinds of that thing happening over and over. And then the other thing is they were very kind to, this team was very kind to include all their files as a step file. And that's great. You can see all the parts basically. It is missing some joints, and mechanical design joints are super important. So, how do you mount this servo to the chassis, and what fastener do you use? What size of fastener? Do you use a washer? Things like that. Those things are important because you do have to source all these components. Now, some teams just like to YOLO it and get like a bunch of fasteners and then figure it out. I personally prefer to map out every single thing. And then the other thing is like a step file gives you access to the parts, but not the assemblies. So what let's see if I can show you here. These are pictures. It looks nice. Again, the body's too fat, but the step file gives you access to the parts, which is great, but what you don't get to see is the assemblies, the sub-assemblies, how things come together. So this is what they have here. And the joints, right? So if you wanted to actuate a leg, there's like a screw, and then there's a part that moves around that screw, that kind of stuff, or your elbow is a joint, right? On a step file, your elbow wouldn't move. It would just be elbow, and then you have to define mates on a CAD software for it to actually move. So I said that I started working on these on August 25th. That day, all I did was open the step files, separate it into parts, and generate a file with mates. So I'm gonna show you what I have right now. The bad news here is that because I don't work as a hardware engineer anymore, so I don't have access to any fancy software. We're using Onshape. It's onshape.com. It is a free CAD tool that anyone can use. There's also Fusion 360, which is free. I personally think all of these free CAD tools suck compared to when I first studied engineering, we were using SolidWorks. Then I went to work in aerospace and automotive, and we were using CATIA. And those are very powerful suits and fully fleshed out, lots of features. Onshape is kind of like, not fully fleshed out yet. So you will see me struggle doing very simple things, and you might think, oh, it's because he's a noob. And that's true. I am a noob when it comes to Onshape. When it comes to CAD, though, I probably have over 100,000 hours doing CAD. I love CAD. So this is what I have. You can see that I only have the leg right now, and today we're gonna focus on building a leg. I also already ordered some servos. These are the servos. I'm gonna talk a little bit about actuators in a bit, but anyways, you can see that this is the same leg as they have here, except I've removed the dingo branding, and I've also recreated the mates that I was talking about earlier. So this leg is fully actuated, all the joints that are there, and so you can do things like this, for example. You can move it around, and you can see that the dynamics of the two servos at play. So there's actually, this has 3 servos here. You can see 1, 2, and 3. So those servos here are exactly these. I haven't actually verified that they did a good job at modeling the same servo, but these are the same servos that they quote on their open source paper. And yeah, you can see how it moves, and basically you have one servo that controls this part of the leg, one servo that controls this part of the leg. And how do you know which one does what? Well, I mean, you can kind of see it here, the 4 bar, but we can also, for example, we could fix this part. So right click here and fix it. So now this one move, and you can see when it doesn't move, the lower part of the leg doesn't move, but this upper, that's what I'm calling it, does move. And so you can see this servo in here moves the upper, and then if we undo this fixing, fix it, and then we fix the other servo. So maybe here, I don't know, I don't remember exactly how that mates are done. You see this doesn't move anymore, but now now these moves. Oh, it's a little laggy, like I said. On shape, man, like not my cup of tea, but yeah, you can see, and it's a little laggy, but you can see how that servo actuates here. And so technically you could get away with only one servo for a leg, and like and have the kinematics almost like hard coded using linkages. But for us, it was very important to have independent servo controls for each segment of the leg, because like I said, we want to be able to dig a hole. So think of like how a dog digs a hole, right? It needs to be able to actuate both sides of the of its leg, like basically this part of the arm and this part of the arm to dig, right? And then we probably need claws there, but yeah, so that's why we chose the Dingo, this open source project. Other open source projects use only one servo. And then this third servo, actually, I don't have it mapped out anything because this would be constrained to the chassis, which is non-existent right now. But the purpose of this third servo is to actuate the shoulder. So this shoulder can move, if you're seeing it just like that, it can move this way. And that's very important. It gives you a little more stability. You can do things like walk sideways. But most importantly for our project, I'm gonna stop saying most importantly for our project, you can use that to do all kinds of animations and make it again walk in a funny way, for a lack of better words. By the way, OnShape keeps telling me I have over-constrained mates. I cannot figure out why, but everything seems to work. So anyways, what we're gonna do today, the purpose of the next hour or so, is to get all of these parts ready to start printing. And so you might see these parts and think like, oh, they look good, right? But again, going back to my point on not trusting open source designs, is that I don't know for a fact that the size of the holes here are good. I don't know for a fact that the bearings they use, I can get from McMaster or a different source. So I'm just gonna verify all the hardware here and make sure we can source it and everything's good, so I can trust this design and we can start printing it right now. And then there's some simplification I want to do. For example, they use these push rods here, which looks like a threaded. Looks like a thread, and then they have these things with ball joints here, which is it's cool. Ball joints are great, gives you some compliance if things don't align perfectly. But I don't want to be sourcing like threaded parts and cutting them to size, so I'm going to replace those with a single 3D printed component. So that's also what we're going to do today, and hopefully at the end of this video we're at a point where we can start slicing it and we can start 3D printing it. I have my 3D printer down there, And I'll show you guys that too. Now, if you do know something about robot docs, you might know that the things like Boston Dynamics, for example, doesn't actually use servo actuators. And then there's the MIT Cheetah project. This is actually, I would say, this is what we're aiming for in B2. You can see here what kind of actuators they use, and these look much more like motors. Like again, let me pull one BRB. Those are more rounded motors, right? Those are the kind of motors that you would find on a drone, for example, right? Where it's like this motor, which is just a regular motor that spins. So it's a bigger motor. They probably have a planetary gearbox. It gives you better control, better torque. It just complicates a little bit more the actuation and the control of that actuator. So that's why we've left it for B2. B1 is just about, you know, verifying that we can basically, what we're trying to risk in B1 is not the hardware, right? So I'm taking very low risk on the hardware side, and we just want to de-risk the model training, the control, the training of the controller that's gonna control this robot. So I'm keeping it very safe with the hardware. So I'm just went with servos. Now on the inside of the servo, actually, it's very close to what's happening here, except, you know, in here there's a motor like this one here. I think it's brushless as well. So like a motor like this, a DC motor. In here, it's very small, and then there's a whole gearbox that makes it so, you know, it spins less fast but with more torque. So that's the next question is like, okay, how much torque do you need to actuate a leg like this? And I actually did some very simple math. Let me pull it up. I have it on my Notion here. By the way, eventually I'm gonna stop talking soon and we're just gonna get to work. But I did some very simple math, which is basically, you know, okay, how much force do you need to move this leg? Assuming the highest load scenario would be, you know, if the leg, why is it not moving? Did I fix something? Oh, is it still fixed? We're just having fun with the, this is fixed, unfix it. So the highest load scenario you can imagine for, first of all, you can imagine that the servo that does the most work here is going to be this servo here that actuates the upper. The next servo only actuates less, like a smaller part of the leg. So if this servo for the upper is good, all the others I think should be good. So I only did math for that main one. And the highest load scenario would probably be when, you know, the leg is fully folded like that and it's carrying the whole weight of the robot. So when you're doing the math, you know, you're counting, okay, what's the mass of the leg? What's the mass of the body? What's the weight distribution? And that's kind of like what, and then what's the lever arm over which that servo is actuating? And so that gives you kind of like how much torque you need. And then you just make sure that the servo you're getting has enough torque. Now on those calculations, you should be a little creative. And for example, when we're distributing the mass of the body over the legs, yes, we have 4 legs, but we have to account for things like, you know, mass distribution of 50%. So half of the mass of a robot is going on each leg. And that's key for things where, like, imagine if your robot dog is standing on only 2 legs. You want to make sure your actuators are not overpowered. And so that's how we end up with this number, 3.51 Newton meters. And then you go and find a servo like this that has enough torque. This is a Hobby servo, right? So first of all, they don't talk in Newton meters. They talk in kilograms of centimeter force. And you have to do some unit translation. And then these are Hobby grade hardware. So it's not like you can fully trust the numbers, and this came from AliExpress, so so you put a degree, a margin of safety there. But this should do the job, and this is just a basic PWM control signal. So anyways, that's how we end up with these. I have 3 of them, so I have all the parts required minus the 3D printed parts, which I'm gonna get now. Yeah, I think that covers it pretty much. And then we have a BOM document, so a bill of materials somewhere here. Yeah, so we're defining assemblies here, and you know, each assembly has a tab. And so today we're working on legs, AT5000. So we go to this tab, and you can see here we have servo motors. the quantity, the unit prices were $45, and yeah. Yeah, that's basically what we have. And so on this BOM today, I'm gonna add all the 3D printing components as well as all the hardware, all the bearings and stuff like that. So I hope that makes sense. And then because this is the first pass, so I haven't printed any parts yet, I'm not gonna do anything about, you know, wire routing, like, oh, okay, if the servo is gonna be in this housing, oh, how are the wires gonna be routed? You can see the wires here are going through the plastic part. I'm not gonna worry about that for now. I wanna see it in person first. It's 3D printed. It's probably gonna take a couple hours tops to print all this stuff. So it's not a huge commitment, and we can figure out the wire routing on a future iteration. So yeah, I think that should answer all the questions. And so, well, if you want to see me, you know, CAD, and if you want to see me do some 3D CAD and figure out what parts we need and put in the BOM and start printing, stick around. We're gonna have an hour of that now. So let's get started. Okay. So I'm gonna work bottom to top. So in the bottom we have these feet here, and so for example, I don't know, should I narrate all of these things? Actually, let me grab a drink. BRB. All right. Let me grab some calipers as well. If you've never CADed something before, you know, calipers are your friend. You know, there are these things where you can measure anything down to millimeter precision. And so, for example, when you're using a servo off the shelf, you're gonna want to replicate this model in your CAD to make sure everything's good. And so you can just measure these in, you know, for example, this flange here is 2.57 millimeters, and you can add that to CAD. And so if we check here, this should be around, you know, 2.6. And you can see down here it's 2.5, so close enough. But again, off by you know 0.07 millimeters, it's probably not a big deal. But always good to double check that your model matches reality to a good enough degree. Anyways, I want to start. Enough talking. I do talk a lot, and that's why I like streaming. I don't know. I think when I see people work on things that I don't fully grasp, I do enjoy the details, especially when, you know, if they grasp it better than I do. By the way, I don't know if you're on Twitter, you might have noticed a trend that everyone seems to be building robots nowadays, which I think is pretty cool. But okay, here we go. So, so this assembly, okay. I'm gonna name these feet. And we need 4 because we have 4 legs. And unit price, I'm gonna put it at 0 for now. 3D printed. Okay, so this guy here, foot low profile. Okay, feet, low profile. I'm gonna keep the same name on my BOM as in CAD. I think I can rename it. I'm sure I can rename it. I don't see renaming. Okay, well. It's an external resource. Okay. Anyways, 3D printed plastic part. I'm sure it's fine, but let's take a look at the hardware here. And so we can see here, this is a M3 bolt, M3 6 millimeter socket head, and we need 4 of these nodes used in feet. All right. We should be able to section these. You can't see it. Like I said, I'm gonna look like a noob throughout, but I really do not mind as long as that means that everything's gonna work out just fine. I am actually kind of curious to see if anyone actually finds this useful. Okay, I cannot mate it, but I can make it transparent, and yeah, it looks like it's a perfect fit. I am a little worried that this rectangular feature is too tight for the socket head. So it's a 6mm cylinder or boss, or yeah, and it's a 5.5mm socket head. So there should be enough clearance there. For hardware, when you're not sure how much clearance you should have and if they model their hardware correctly, I like to go to on like Mastercar, and then here we can find an M3 with standard thread, a 6mm length, and just pick any, and they have drawings for all of these. And you can see here their head is actually 5.5mm, so it looks like it looks good to me. I'm gonna close some tabs here. Okay, so that looks good to me. The other thing I want to check is that that 6mm has enough thread engagement, and so that doesn't look like enough thread engagement to me. You kind of want to have at least 3 threads of engagement, maybe up to 6. Anything past that, it's not really doing much, and so I think we might want to go deeper here. But let's see if we have the space. So you can see here with our thread and our screw is not going all the way in, and we actually have another 2mm that we can go into. But these are feet. I'm gonna let that slide for now. So I'm gonna keep with those 6mm. And anyway, so the feet look good. So I'm gonna call this part good. So anytime I see a part that is good, the way I'm gonna remind myself that I've already checked this part, I'm gonna paint this green. So you can change the appearance here somehow. At least, okay, section view is there. Now we know. You can usually change the appearance somewhere in here. No, see, on SolidWorks it's on the right, but again, looking like a noob. I'm gonna Google this on shape. Apply color to part. Changing on shape. Right click the part. Select edit appearance. Was there an edit appearance? Edit context. Make transparent. I cannot see a. Guys, do you see an edit appearance? I feel like it must be right in front of me. Maybe if I double click it. No context. That's not good. Cannot release it. Editing. So it's a linked document. I think that's what's we'll change it on the link document. Oh, we don't have the link document. Interesting. Yeah, just a second here while I actually figure out how to assembly. So it wants me to open the part studio for this part, but I don't think I have that. Okay. Anyways, another way of keeping track of what I've already checked is just hiding those components. I don't know if that's great, but anyways, that component is good. Eventually we want the entire leg to be hidden. The next thing here is this threaded insert. So it looks like a M3 threaded insert. We're gonna need 4. Let's isolate. Threaded inserts are sourced also in part by their length. So I'm gonna write 4mm deep and write using fit. Okay, so I think that looks fine. Oh, let's double check. So you want to check the fit is good. So the outside is 4.2mm diameter, and so the inside here should be, maybe 4 tops. It's 3.8. So I'm happy with that 3.8 fit. The one thing I would change here, I want to put a chamfer here. let's see if I can modify this part. See, that could be an entire different thing. If I can't modify this part. Okay, I can modify the part, that's good. So I want to put a chamfer, so when we're putting the heated insert, it kind of like guides it in there. So I'm going to put a chamfer here. And so here's the chamfer. I want to add a chamfer. Now adding chamfers is basically quote unquote free because, you know, it's just a 3D printed part. So, you know, I can just add pretty much whatever I want. Now do keep in mind that we only had 2 millimeters of thread engagement. So if we're adding a chamfer here, we're losing some of that. But even a small chamfer would be fine, like 0.5, because we just want to guide it in. So that's it. Okay, perfect. And how deep is this hole? Looks like it's 6.5 millimeters deep for a 4 millimeter insert. So that looks good. I trust that. So that's good. And so we're going back to the assembly now. So, okay, perfect. It updated. So that looks good to me. Actually, I already have some inserts, so let me just measure that one and make sure it matches this one, so we can just reuse parts that we already have, and we don't have to order more. All right, so I have some M3 inserts already from my previous projects. So I'm just gonna measure these. It's funny, yeah, this is also from AliExpress. None of them are labeled, so great. But let me just check how deep are they. So we should be looking for a 4.2 millimeter depth at least, and up to 6 millimeters. So this one's 5 millimeters, so I think it'll be fine. So, so I'm gonna call that good. We're gonna move on. The body of this leg, you know, it's not a huge deal, you know, it's like just a prototype, so it doesn't really matter. We could change the appearance, simplify the appearance for printing it. The only thing I would say, it's not great for printing. When printing, you want a flat face, so we'll probably print on top of this face and place it like that on the printer. And I think that's gonna be fine. Ideally, I would like to print like this. So the holes for the key joints, so this joint is very important and this joint is very important here. So those holes are very nice and rounded. When you print at an angle, they won't be as rounded, or when you print like this, they won't be as clean, because, you know, you're basically stacking layers this way. And if it's a hole and you're stacking layers this way, those are gonna have some texture, not gonna be as clean as if you were stacking layers in the same direction as the axis of your hole. But for this, I think it's fine. So the next thing I'm going to check here are these joints here. So what we have here, oh, actually let's add the leg. So if this is the upper, if this section is the upper, this should be the lower, leg lower. And this will change depending on if it's the right side or the left side of the leg, right side of or left side of the body, right? Because it's going to be a mirror on the other side. This is the right side of the body leg, so I'm gonna add right to the name. Perfect. And we need 2 of those. 3D printed. All right. So next we're gonna see this hole here. So it looks like we have an M4, 25 millimeter long. So I actually don't have those, and that's a socket head. So I actually don't have that in house. So we're gonna have to purchase some of them. Those are 4 used in like in knee joint. 4 of them, and we're gonna repeat the same process. You know, making sure we have enough clearance. You know, 8 millimeter hole on a for a 7 millimeter diameter socket head. So again, that looks good. So whoever cut these, I think, did an okay job. And on the other side, it appears to be another threaded insert. So let me check that threaded insert again. So 5.8 millimeter hole, hide it, and the outside of it's header insert is 6.4. I do have to have some M4s here. Mine are 6 millimeters. So that could be a little loosey-goosey. And wait, we said, what did I say? The outside is 5.9 on this one, and the depth is 6 millimeters. So I might want to make these a little tighter. Make a note of this. Threaded insert. Where I need 4 of these. Anyways, I think that should be fine. Let's find the lower profile. Where's the here? I want to isolate this part, see what it looks like on the other side. Again, I'm gonna be looking to add a chamfer here somewhere, probably on this side. So let me just go do that right now. So you see me jump in between assembly and part studio. So that's just how Onshape works. So when you want to make a change to the part, you go to the part studio. You cannot change a part in the assembly. So I'm gonna add the same chamfer here, 0.2. Again, very small detail. You're probably fine without it, but like I said, it's free to add a chamfer. So why wouldn't you? Okay, so that insert looks fine. And actually, that insert doesn't look fine. Let me tighten that hole. So one thing that it's way easier to do is to make a hole bigger in real life than make it smaller, right? Because you can just drill it. And so my inserts are 6 millimeter outer diameter, and so I want at least I want to make sure there's not too much clearance. So yeah, we have 0.2 millimeters of interference. I'm gonna call that good for now. Like I said, B1, first revision. We can always come back and clean things up. So this joint looks good, but we cannot just call the part good. So we need to check more. So now we have some bearings, so that's interesting, right? So first of all, if this is a regular socket head, and they have AS 14020 socket head. I don't know if that's a shoulder bolt. It looks like a full thread, and so it's not ideal to have threads be the interface surface to a bearing. But this is not a high-speed application. I'm just saying it's not ideal, especially if these are plastic bearings. It says thrust bearing here. So what I want to see is, first of all, where can we find these bearings? And second of all, how these bearings are fitting into our leg. And so they're not fitting in our leg. They're kind of like floating in between our upper and lower, or they're fitting on the lower. And you can also see here that there is clearance, 0.3 millimeters clearance on each side, so a total of 0.6 millimeter clearance. And I'm a little rusty on like if that's a lot. I think that's just fine. So it kind of like gives you a little float, and then you can think of like when you put the socket head throughout here, it will compress it and everything will be in contact, maybe. Or maybe not, but I think it looks safe. So I think I want to call that good. Also, I swear I added a chamfer here. Oh, there's my chamfer. Is that a chamfer? Yes, there's my chamfer. Some people might think like, I'm being too picky here, but again, I've been beating in the past, so I need to do this. And so while we're at this joint, let's also check how it fits here, how the bearings fit into the upper. And we can do a section view for that, and this is how they fit in the upper. I'll very much like this fit. you know, this is not the tightest ever joint, but like I said, low speed and you know, 3D printed parts. It's not like the tolerances are going to be decent. There might be a little bit of play, but very subtle. And so now let's try to find, where did these guys buy these thrust bearings? I don't think I can copy paste the name. No, so thrust bearing F410 410 4. So Google's your friend. 410. That looks exactly what they had there from Boca Bearing. So these are steel, chrome steel, so that's good, right? We remember how I said it would be nice to have a plastic bearing go into the socket head threads, so that's good. Except I've never heard of Boca Bearing, so ideally we keep everything to one supplier. So let's see if McMaster Car can help us here. They also call this a thrust bearing. Yeah, I mean, it's kind of overkill with all this stuff, but let's try to source one from McMaster. 4mm inner diameter. So these are metric. Shaft diameter here, 4mm. And ID4 OD. So the outer diameter we're shooting for here looks to be 10. That's on the name before, by the way. It's all in the name here, but I'm a little rusty. 10. And we have two. We have light duty for $199, and then we have the super overpriced you know, bronze cage, or we have some plastic here. Yeah, so let's see. So these plastic ones are, oh, it's basically like a washer, a plastic washer. Probably don't want that. This looks closer to what they use. The full sandwich is 4mm here. You can see 4mm sandwich. Let's see what their dimension here is. Their actual length, 4mm. So, I mean, this will do. Even though I know for a fact that, you know, this is like overkill, way overkill, but and it's 866 each, right? So I might just go with it, being lazy. Let me just see, you know, if we don't care about the OD, but we thickness. No, see the thread. Yeah, we want ball. We don't want plain. Okay, I think we're just gonna have to pay. So I'm gonna add thrust bearing. Using knee joint. We need 4. Unit priced 866. The one thing to know with McMaster is that unit prices are. It's a trap because yeah, 866 plus tax and then plus shipping, and the only shipping McMaster has is basically like next day FedEx, so it's actually pretty pricey. For that exact same reason, you want to make sure you don't miss anything on your McMaster order. If you do, you can ask them to consolidate orders, but they ship really fast, so you gotta catch it early. And we actually need 8 of them because there's 2 on each side. So that alone, it's $70. You know, that alone. That's an outrageous amount of money for what it is. Yeah, I'm very tempted to redesign this joint. But, and so, you know, if I was redesigning this joint, I think ball bearings would be just fine. Let me think about it. Can we do like a ball bearing. But see, we can definitely get way cheaper ball bearings. Oh, by the way, when you pick McMaster cars, get the part number in here. So it makes it way easier to source later on. All right, so that's the one. But you know, we could redesign these to use a ball bearing. ball bearings can be much cheaper. And just to make the redesign as easy as possible, let's try to see if we can find something that is already kind of like close in. Okay, no. So the ball bearing is gonna be thinner, but that's fine because we can really move our 3D printed parts to be anything we want. Let's keep the shaft diameter the same, so it's just to not be like super disruptive here to our design. And now I'm shopping for price. All right, guys, maybe I'm just out of touch and bearings have gone expensive, or you know, maybe we go for plastic here. All right, I'm gonna let this go. I can't find an easy solution here. Maybe we just go and get some bearings from AliExpress later on. But like I said, it just feels so overkill. I don't think we actually need those fancy bearings. But other than that, this drone looks good to me. And we have sourced our bearings. And so we can keep going. And let's get rid of this section view. Let's see if I can figure out how to get rid of this section view. Section view. I cannot seem to get rid of this section view. Okay, that's one way of doing it. Okay, so those bearings are fine, so I'm gonna hide those bearings. You know, so far everything's going good. And then since we're working on the leg lower, we should also check this joint here. Now this joint is one that we do have to redesign. So I'm gonna leave that for later. And I did say I would make the parts green when they're cleared for 3D printing. So I'm gonna make it green like I promised. In this channel, guys, we always keep our promises. Now, of course, that means I have to figure out how to actually make things green. And it's like, is that the good shade of green? That's a good shade of green. We're going back to the assembly. Give it a few seconds to refresh. It's kind of funny how it takes a little while. This is all in the cloud. It's happening in the cloud. In the cloud, guys. Okay. Next. See, this is we started on the easy parts. Now we're getting more complicated. So next, we can check in here, see what's going on in here. And so let me hide these. Okay, so that's a bearing. This says it's a washer. I don't think that's a washer. Is it a washer? All right, so there's a washer going straight. Oh, okay, washer sitting on top of. Okay, so first of all, there's a washer with holes, but see, like, there's no fasteners. So I don't know how this washer actually attaches to this servo disc. And so first of all, I think these servo discs are included with the servos I bought. I'm assuming we all bought the same servos. And so I'm just gonna measure it, make sure. So there is a disc here, servo disc. Looks like a cheap ABS part. And thickness 2 millimeters. Whoop. Oh, is it? What is going on here? Looks like there's no clearance to that orange housing. I just so they have it at 2.5, which is not true. It's 2. There is a flange though. It's a flange. I don't know if I measure these. That's clearly at 2. So you know, these small discrepancies actually add up. And then the outer diameter, it's at 20. I'm measuring 21. Okay, and then they have 4 holes on their thing. I have 12 holes on this one. So maybe not the same after all, but that's the only circle that came with that thing. So the good news is that this servo disc can be easily 3D printed. And then after that they have, okay, a screw that screws the servo disc into the servo flange head. That makes a lot of sense. It's a good, nice fit. And so we might have to just 3D print that servo disc also. So not to worry about that. But let's get back here to what we were actually doing. And so if we're 3D printing the servo disc and we put in a bearing washer on top, I think we might as well just turn all that into a single part, because why wouldn't we, right? We can just make that, these two, one part. And that will reduce the BOM by one part. What else did we have in here? Not the thrust bearing. Servo cam, the cam. See, in SolidWorks, there's a way to only show the hidden parts. I don't know if there's a way to do that here. I was also a bit worried. So there's clear interference in between the servo disc and the housing here, right? This right here, and then this right here. So I don't know what their plan for that was. You just like YOLO it. So we're gonna want to fix all of that. Yeah. Fun. More work for us, guys. This is why AI won't replace us. JK, AI will replace us. I'm trying to bring back all the parts here. What else am I missing? Well, I'm missing the upper, of course. And didn't we have one more thing? Well, the upper actually has 4 holes also. And so these 4 holes go in there. And just judging by that, they didn't put fasteners, but it looks like they want 2 socket heads go in here. And I guess this servo disc is somehow threaded into that. But, you know, oh, you could thread into this, but you just gotta be very mindful that the clearance for those threads, like you cannot overshoot the part at all, because that servo is right there. So that's totally fine, except, you know, that's a very thin part. We're talking, this looks huge on CAD, but in reality that's like 2 millimeters. So yeah. Anyways, I think what I'm gonna do next, so that looks like quite a bit of work actually. So what I'm gonna do next is I'm gonna replace this part here. So this entire assembly thing we're gonna replace. Let me see if I can open it. I cannot open it. Okay, so this is not hard to replace. So so first of all, there's an M3 bolt screw running through it. Why can I? Okay, let's isolate these and let's measure axis to axis. Can I measure? Can you let me measure? Yes. Oh, wait, that wasn't the measure. I thought M was for measuring. M is not for measuring. M is for mate. That makes sense. So we're gonna measure here. Boom. Bam. Parallel distance 130.2. I'm gonna write name here. 30.2. And 4 holes on the ends, and 4 clearance, what, a 4.4? Wait. Oh, M3 clearance. 3.1 is tight. M3 both ends. Is it both ends? M3 clearance. Yeah, it's an M3. All right. So now we're gonna create a new part. I think I can just open Part Studio here. We're gonna call these, what should we call these? Pushrod 1, pushrod upper, pushrod upper. Pushrod upper. Is pushrod one word or two? I think it's two, right? Yeah, pushrod is two. So we're about to remove quite a bit of parts, guys. So that's always a win. And so, all right, quick little sketch here. Top plane. I try to, you know, pick an origin that makes sense, use planes that make sense. Everything has to make sense. We do things here that do make sense. Oh my God, how do I measure? What a, sorry, no swearing. What a rookie. L is for line, I got that. D is for distance, of course. 32.2 millimeters, and we're gonna make these holes 3.2. They had it at 3.1, but I think that's very tight. 3.2, and then this is supposed to be a construction line. Construction, boom. So construction line means a part that doesn't define the well, it does define the geometry, just doesn't define any edge of the solid. It just defines features, geometry of features in there. So that's what our part looks like right now. And I think this is going to be very simple. I think there's a slot. Okay, SolidWorks had a slot feature. Come on, guys. Come on, Onshape. You gotta have a slot feature. Search slot. Boom. There we go. Slot feature. Perfect. Very nice. Very nice. D. What was there? D. No. I like to constrain. Oh, I like to how is this constrained? First of all, it already says constraint. What? Oh, here it's constrained here. I don't want to define it that way. Instead, I want to define a clearance here, and I think, you know, the wall thickness from our mounting screw. We're gonna go with 4. I think that's plenty of material. And if you want to get fancy, you know, you could carve out some of the inside and stuff like that. Probably not gonna do that. And then, oh, the other thing I didn't check was how much clearance we actually have for these. So first of all, looks like, I wonder if these two planes are actually in line. So they're out of line by 1.95. And I don't know what's causing that. But that's fine, because we can always add washers and stuff like that. And how thick were these? These were basically 3. And so our pushrod upper, guys, can be 3 millimeters thick. This is basically what a lot of part design in mechanical engineering boils down to. So if you're still here and you're enjoying this, maybe you should be a mechanical engineer. Have you considered that? And now let's just get fancy here with chamfers. Chamfers are, of course, the true sign of a master here. Okay. So now we can go back to our assembly and add our new upper. Are you guys excited? Upper. Okay. So we gotta insert the part, which I totally forgot how to do. Insert part, pushrod upper, and you don't just insert it. You also have to kind of constrain it so it's just not floating there, like breaking physics and stuff like that. I actually don't know how to control. No. I'm trying different hotkeys to see if I can rotate the part, but it looks like no. I mean, I know one way of rotating the part, but this was a very slow way. It's like, you know, it's like not nice. Anyways, I don't know why more people don't go into mechanical engineering. It's very, very nice art. Very nice field. It's not art. And it feels like with robotics, mechanical engineering could be making a comeback. And I know someone in the comments is gonna be saying like, I'm doing things wrong. And you know what? I don't disagree. In fact, I would agree that I'm probably not being as efficient as possible. And maybe the best step is just to YOLO the first. Okay, so we replaced that push-rod assembly with this one part. I'm gonna fix this just 1 second so we can finish with this part here. So what I had in mind was this would sit in here. Of course, if that is sitting, if these two surfaces are touching, that sounds like friction, right? So not ideal, but I'm gonna run with it for now. I'm gonna take a lot of liberties because it's the first sprint, and we should be learning lots in the first sprint. Okay, I'm gonna refresh. That should not have broken anything. I don't know why it broke anything. Very laggy, guys. Very laggy. Okay, still broken. So my last mate broke the thing. I don't know why. I guess maybe I don't understand what a planar. Oh, is it because this is fixed? See, it seems to be happy. I don't understand why planar would have broken anything. But yes, fully okay. Trying the same thing again. Definition of madness. Trying the same thing and expecting a different result. But let's see. You never know it on shape. I feel like, oh, that's not looking good. Not looking good, bro. See, slider sounds wrong. It's not a slider, mate. Planar. Solve. Why would this break anything? I don't understand. I do not understand. I swear I don't fix this, so one more refresh. Good luck, refresh. We're gonna need another coffee. So yeah, there's definitely room for better CAD software if you ask me. Good. Where? Okay, I'm gonna remove one mate. Overdefines the assembly. Not true. This is a lie. But I'm gonna pretend it's right. It's kind of like when you're writing code and the compiler tells you an error that it's wrong, but you gotta play along. Like, oh yeah, of course. Okay. Yeah, something like that. I think looks very nice. I do wonder why they decided to put a nut here instead of like a threaded insert like the rest of the joints. I do think your design choices should carry over your part. I was like, why wouldn't they? Unless there's a good reason, a surprise good reason that I want to find out once I'm trying to assemble these. And now let's try this again. Cylindrical joint. Cylindrical is the same as concentric joint in SolidWorks, from what I can tell. But of course, I could always be wrong. Often wrong. And you see, it works now. Ta-da! It works now. And so what changed? Nothing changed. Just the order where I define my mates, which should not have altered anything. But okay, I'm gonna remove this nut here. We're gonna change that to a threaded insert, just like everywhere else so far in the leg. And it's looking. I think it's looking a little sad. This thing. This what did we call it? Push rod upper. So I'm gonna add a little flare, And again, this is entirely for fun. Is mechanical engineering about having fun? Depends who you ask. Do I think it's about having fun? I do. What's the point of life if you're not having fun, guys? Are we turning into a philosophy channel? I feel like we already have way too many podcasts and stuff like that. Thickness. Okay, midplane. Thickness. Give it a 2. Kind of like a rip, you know. Bambo boom. All right, little flare. Right in spikes. Gonna be like a dinosaur. Obviously, we're not doing this for flare. We're doing this for stiffness, guys. If anyone asks. Maybe too much. I'm so used to like jumping between windows, between parts. There's no, I don't know a shortcut to jump between parts here on Onshape. It will be really crazy if like the Onshape team watches these and they correct me. Crazy as in like I hope that happens. That's what I mean by crazy. All right, is that enough flare for you guys? Absolute, so much flare. I don't think that will cause any interference. It adds aura, very nice flare. All right, so I wanna, okay, so before we keep moving on, okay, why is this called part 1 and not upper? What a mystery, what a great mystery. Oh, I know why, Because here in here, the name of the file doesn't define the name of the part in the file, even though you're Part Studio, right? Yes, correct. Intuitive, we're learning. Okay, so we're gonna change this, before we keep moving, we're gonna change this to a threaded insert. These were M3s, and I think this was also an M3. Yeah, so I'm gonna copy the dimensions of this hole here. Again, for consistency purposes, because we should be consistent. And so we said this part was done. I was joking, of course. It's never done. Parts are never done. Okay, it's isolated, but not in a way where it's actually isolated. I don't need to see these. I don't need to see planes. Planes in Onshape I've never found as useful as in SolidWorks. SolidWorks, I was all about my planes. So this is a through hole for an M3 right now at 3.3 millimeters inner diameter. That's a through hole for an M3 on the tighter side, but a through hole nonetheless. And so what did we say? Yeah, I can't see. What did we say this was? I'm gonna hide all this stuff. Hide this stuff. And so 3.8. At 3.8. Okay. All right. 3.8 is open this. Open. Okay. Very nice. Not lagged at all. Okay. 3.8. 3.3. 3.8. Remember that. There should be a move face. Yes. 3.8. So we're moving it outwards. 3.8. Moving 3.8. So it's like 3.8 minus 3.3 divided by 2. I think you can do math here. Yes. Boom. Except we made this the wrong way. So we gotta go the other way. 0.25. This should be 3.8. Boom. 3.8. Guys. Have not lost the touch. Add a nice chamfer because chamfers are free. And that should do, right? I like it. It's getting better already. All right, boom, there we go. So now I want to say that that part is done. That should be done here. Yeah, and then we had an M3. We had an M3 here somewhere. No, yes, you. And so this M3 now is too long. And so this M3 is gonna sit here. Planar mate, planar. There's also the fastened mate. Which sounds complicated. Planar, boom, boom. Okay, nice. Okay, obviously too long there. But I have a box full of M3, so I'm gonna like let that slide for now. And keeping with my, okay, and so that, see this gap here, it's very worrying, but the stack here on the servo disk and stuff like that, it looked really bad. So I don't believe that this gap is real, or maybe it's worse, so I'm not gonna act on it right now. And keeping on with our tradition here, I'm gonna call this part good, and I'm gonna make it a shade of green, darker green. Back to the assembly. Are you guys bored yet? Oh, same shade of green. Okay, well, didn't realize. So next we can either do the cam or we can do the upper. I think both are a mess, so not looking forward. Also, another thing to keep in mind is it looks like we have some interference here. Of course, that's a position that the robot will never go into, I think. So we can always control the limits on software, but it never hurts to plan the failure modes of collisions on the hardware side, right? And so if we were to collide, ideally it will be parts that are not going to get completely wrecked or going to wreck our servo. So the servo horn there was colliding. And so if the servo horn collides like that, we risk stripping because the mating surface has these grooves, and the servo horn is plastic. And so if you over torque and you just push through it, it will eventually strip, and then you will be out of a horn, and then you have to remake a horn. Except these horns came from China, then you have to map it out and print it, and that sounds like work. So as a next step, I'm gonna get rid of this push rod, the small push rod, which sounds like easy work. And so same as before, D4 measure, JK, square bracket for measure, that's of course, and then axis to axis, 37.6. 37.6. And so we're gonna replicate, in fact I'm gonna use the same part studio. I think we can do this. So I'm gonna rename this part studio to push rods, and of course it's also an M3, and in here we're gonna replicate the same process, except now my axis is not as clean. So I don't know, I don't think this is good practice, guys, but it definitely helps with speed. D for distance when you're in part studio, else square bracket for measurement in assembly mode, of course. And then we said, I think we said 3.2 for the M3 through holes here, and then the slot feature, which we don't know where it lives, so I just search it. Slot here, yes, very nice, I like it. Except we're gonna get rid of the default 20mm diameter, and we're gonna put our own wall thickness of 3, we said 4 actually, millimeter. Why is this not full? This is not fully constrained because, first of all, this should be construction, and second, it's not constrained in space because it's no relation with the axis. So this should be also construction, and there should be a distance here, yep, distance 25 millimeters. Okay, why is this not fully constrained? I think it's because it's not constrained in parallel. And so how do we make this parallel? It's usually a constraint in SolidWorks. I'm gonna search it here. I do like how you can search things. That's very nice. No, sorry. Well, yeah, parallel to one. Oh, that's not a good face. Okay, perpendicular. These should be perpendicular to these, I've said. And just like that, guys, we are done with our second part. This does not look like a construction line to me. That is gonna mess all kinds of things. Yeah, that needs to be a construction line. Please, okay. All right. I think I'm getting the hang of on shape. So next, extrude, and I think, no, not like that. Extrude by solid, of course, solid, that's solid. And 3mm, I think we said. Of course, you can always measure it, but it's not as fun as guessing. 3.2. All right, and we could also add flare to these, although this is much smaller. So maybe it doesn't need flare. All right, okay, and just like that, guys, just like that. All right, fine, we'll add flare. We're all about consistency here. Well, actually, hold on, let me, because that whole area is tighter, so flare could cause collision. I see why they have nuts here. This is so funny because these guys seem to be threading into this plastic servo horn, which seems like not the best idea, but it is very tight. Meanwhile, this could have been an insert, but they went with a nut for some reason. So some inconsistencies there, but okay, we do have room for flare, so let's add a rip. Very simple rip, very nice rip. Okay. Of course, this rip should be centered, and this should be a construction line. And I do realize, definitely, it doesn't escape to me, the fact that there's probably a simpler way to constrain this. I'm gonna use this face. That's bad idea usually. A tenor, another tenor here, so it's symmetrical. That's the wrong tenor, minus tenor. That's the right tenor. Okay. Well, that rip's gonna be too small, so tenors doesn't work. We're gonna fives. That is the wrong 5, minus 5. I don't know why it keeps doing that. 5. Oh, I see. It's not symmetric. All right, D for distance and a 5. That looks too thick. I think it's a 2 and a 4. Like I said, you can measure, but guessing is a lot more fun. Should we put music or am I get copyrighted? All right. And then you name your part. Don't forget. Push rod cam. It's not an actual cam, but they call it cam, so I'm gonna go with it. And now we can delete this part here. Elon would be very proud, deleting parts. And then we can insert, Control C, Command C. Wait, oh yeah, insert a part, push rod cam. Okay, we still haven't figured out how to rotate without going this way, which is very slow, painful. So if someone knows a better way to rotate, please comment below. Okay, so now we have a couple cylindrical mates. Make your cylindrical mate to the cam itself, not the fastener, because the fastener might, we might remove that next, who knows. And okay, and okay, here we might be screwed. Can we hide this, please? Okay, hide this. When making mates, you always want to be thinking of, be strategic, right? You want to make it in a way where, like, if a part was to change, it's not going to completely destroy your assembly, else you're going to spend hours rebuilding your assembly, and that's not fun. And see, now that we have this part, we can actually increase the clearance to the cam by curving it if we needed to. We probably don't need to, but I'm just putting it out there. And so that could be all the way down. Do we even need these nuts anymore? Should we just remove? Oh my god. Oh no. That should never happen. The knee went backwards, guys. That looks painful. I'm sorry. All right. Back to normal. All right, so see, funky things are happening. Whoa, whoa, whoa. Okay. I think you can define angle constraints on some of these mates, so that never happens. But yeah, what just happened was something very painful for the robot. Hopefully, it never happens again. I'm gonna make this touch here. Yeah, and I think that will work. I'm gonna eliminate this nut here because this really should be a heated insert, just because heated inserts are everywhere else and I like consistency. Yeah, let me just verify. Okay, first of all, 1, 2, 3, 4, 5 holes. Let's see what horn we have here. Yeah, so this is our horn, and it indeed has only 4 holes. So maybe they're 3D printing their own horns, which would be fine by me, honestly. Sorry, I'm getting a text.
2,000 years later.
All right, we're back. So I think this part is fine. So I'm gonna turn it green, following convention here. Different shade of green. Not to be confused. Different shade of green. All right, so we're making good progress here. Really, the last 2 parts that I need to be, the last 3 parts that need to be done are these, and that. And maybe update the faster at least after. So next, oh, I guess this part as well. Oh, man, yeah, it's been an exact hour since we got started. All right, anyways, stop complaining. Section view here. Let's just understand here the upper. Let's finish the upper, flash it out. So it's like a bearing here. Now the question of this bearing here is, how did the bearing get into this cam, the black part? You know, because it appears like there will be no way. You would have to like press this in, and looks like well, obviously there's interference if it's coming in this way. So this groove here is 29.4, 29.4. So that's a 1.5 millimeter interference pushing this bearing in. So the question is, will the plastic comply? Because that bearing looks like metal. 1.5. It's gonna be tough, but I could see it. The other way you could do it is pause print, put the bearing, continue the print. But I'm gonna print this before I get the bearing, so probably not. Anyways, we don't need that for the upper. On the upper side, the bearing fit looks a little tight, but technically no interference. Oh, there's some clearance there. On the upper side, I want to say it looks good, and obviously this hole is just for clearance to the socket head here. And it looks good too, with 5.7 diameter for a M3 socket head with a 5.5 millimeter head. So, you know, tighter, but these guys have really tight things here. I want to say the bearing on the upper side looks fine. And we already cleared the joint here. So the upper should be fine. It is very beefy. And then we have these holes here. 3.5 millimeters. See, like normally they go with 3.2. For some reason, those were 3.5. I don't know. Yeah, I want to say the upper looks fine to me. And it's not just because I'm rushing, guys. It's not just because I want to go eat lunch. It actually looks fine to me. Okay, I made that green, but it doesn't look green. Is it gonna be green? It's not green. Guys, I made it green. Why can't you add appearance in an assembly? So if someone works in Onshape, can you explain this to me? Okay, I made it green. Do we agree? Yes, that's the upper. I'm puzzled. This is the part, yes. Refresh. Even refreshing takes long. Okay, it's orange now. Is that closer to green? Okay, still not green. But it says it's green. So is there something that overrides these somehow? Like a part level appearance. Okay, I can't find it, but and also I lost our assembly now, so let's go find that. All right. Okay, not green. Okay, fine. Not green. All right. So next, let's look at the cam. So like the cam. Actually, this part here might be the only one that's also just good to go right off the bat. I don't see needing to modify anything other. Oh, actually, should check clearances. See, like that obviously it's interference. Like how? Anyways, I'm not gonna judge. The cam looks fine to me, other than like the bearing part, and I've never tried to push a bearing into like something like that. 25, 32, 4mm bearing. Let's see if Backmaster has this. I mean, looks pretty standard. Sorry for the noise. Let's isolate the bearing. Let's go bearing shopping. Inside diameter 25 on the dot. So it's a metric bearing with an inside diameter of 25. And looks like a ball bearing with an outside diameter of 32. Does that mean housing ID? I am not entirely sure. 32. Oh wow, that's expensive. That's expensive, guys. That's ultra thin bearing. That's cheaper. I mean, that one looks ultra thin to me. All right, I'm starting to think Backmaster is not the place to buy bearings. But see, deliveries by Monday. It's so fast. It's so convenient. Why wouldn't you? Made in Japan or China. They cannot tell you. It's a secret. 32, 25, and 4. So like, what is the depth? 4. Perfect. So let's add here cam bearing. We need 4. Very expensive bearing. 37.49. Backmaster. I'll just tell you now. You know, we started this video saying the budget for the entire build was 1K, 2K. I can already tell you I'm not spending $200 on bearings. That's just not. It's not something that's gonna happen. But let's just keep it rolling here. And I think with that, the cam is fine because the clearance there is fine. We just need to figure out what's happening with the servo mount, but everything else on the cam looks fine. There's like a fine groove. Oh, actually, not everything else. We did say we were gonna put heated inserts here. So this nut goes away, and so a 4-hole on for a 3. See, that makes no sense. 4mm diameter for an M3. That's a lot of fluid. It's very loose. Especially considering like they were giving like 0.2mm clearance for the M3s down here. So I don't know if I'm missing something or what's happening here. So I think this was also M3, and we said the hole was gonna be 3.8. So these are part of M3s, right? So we're gonna change this servo cam to V, or not to V, 3.8. All right, so we're gonna move those face, move face. So remember math, 4.1 minus 3.8 divided by 2. This one and that one, and they're going this way. So now, oh my God, no. All right, so now, oh, wrong direction here. And, oh my God. All right, wrong direction for sure. Easy fix. Click here, click there, beep, bop, boop. 3.8. And guess what else we want to do, guys? Who said add a chamfer? You win. We're gonna add a chamfer. Small chamfer. And why are we doing this again? It's because chamfers are free. So we add chamfer, boom. All right. So now I think I'm happy to call this part done. Done. Yeah. I think we're moving faster. And what do we do when a part is done? We make it green. That's correct. All right. So now all the parts are green. The upper is green. It's a grayish shade of green, but still green. And then we could check the housing here. Even though I am very hungry and I would like to go eat. And then, yeah, I still need to clean the bomb because there's a lot of fasteners missing, and it sounds like I should be placing an order for fasteners. The other thing, I could just go to Home Depot and, you know, get the lowest grade fasteners and see if things work out. Yeah, so I don't know what's going on. Okay, what about, I don't know if these are custom horns or what's going on here. Let me check. So that's 5 volts, and again, this doesn't match what we received from our servo supplier. So I want to say these are custom, or they bought them somewhere else. But I'm supposedly have the same servos, and so if they're custom, did they do a good job? Because that is an interference fit. You probably want to apply this with some heat. And well, obviously there's interference already. See, for that particular servo, it's probably fine. This one is what's worrying me. This obviously clearance for the wires, it's in shambles here, not great. But other than that, keep getting texts. Other than that, the head. Let's see, like there's so many interferences that I really don't know if this can be trusted whatsoever. But other than that, and like I said, it's really, you guys are seeing it really comes down to the joints. There's so many joints, so many little fasteners, and it's only one leg. It's one leg. So okay, so I'm gonna ignore the horns for now. Ignore all the servo related parts because those are very small. We've already cleared all the big parts. I don't know, am I being lazy or should we clean this up? This is technically a servo horn. Why did they do it like that? I guess they don't expect it to go this deep. So this can come up, and if this comes up, this will be great. Yeah, I'm very tempted to proceed as is. All right, so I think the next step is to, and I've never done this before, so bear with me, but I think we're gonna try to print some parts right now. and after that I'm gonna go have lunch because I haven't had lunch and it's almost 3. So this is our printer. The Bamboo printers have a camera inside, so we can see inside the printer. Very cool. And you can upload a part. And in STL to like kind of print it. And so I'm gonna start with the obvious, well, with the green parts. So obviously, let's see how many we can fit. We'll print one leg, one full leg. So let's see if we can export these as an STL. Yes. STL, perfect. It's like a nose. STL, just throw it in here. And let's see what happens when we. See, I don't know how it says publish model. It doesn't look good. Node, okay, like simple, still okay. Next step. Wait, I don't want. I guess I'm publishing this to the internet. Upload. See, it wasn't trying to upload. Global process. Select. Add a part without uploading to the entire internet. Add. Oh yes, easy. Okay, that looks good to me. Now the question, of course, as always, is how do you rotate it? And we have a very janky interface here to rotate. I don't think that's the best way of rotating things. There's got to be a better way, right? Bamboo, please tell me you have a better way. There should be a way to snap a yes, lay on face. Lay on face, boom. Okay. And now we can rotate just to be mindful here of the space. So if we print it this way, we'll probably need some support. Wait, that doesn't look flat whatsoever. I chose the wrong face, guys. My bad. Here, this face? No, not that face. This face? Not that face either. This face, yeah. Yes. Yeah, that looks good to me. Okay. All right, so that's one part. Right? I mean, no, okay. All right, last time I changed this, that way, right? Okay, and now we gotta export all the other parts. And soon enough, we will have our full leg in here. Don't forget this little guy. I don't see the export. Oh. Okay, there's a permissions problem with that part that I need to fix. Can I export all of them in one go? I don't think that worked. Oh, right leg assembly. No. See, I think it was trying to export them all as a single part, which is not ideal. We have that one. Unclear to me what just happened. Export, save that one. Okay. Export, export. Export. And export. And see if we can also export this one. It looks like there's a dependencies issue since it's an import. Let's see. Nope, it's fine. Boom, here we go, we're in business. All right. So other than like the feed, everything else has been exported. I just need to figure out the servo horns. That won't be a huge issue. And we can start printing right now. So very, 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 very exciting. Very exciting, guys. Only took 1.5 hours. let's see what we have here. So obviously this one already good. This one we're gonna print. So that would be painful to print that way. So let's print on this face. These guys. Oh no. Okay, so these are, we have two of the same. Oh, I see. Okay, and this guy should be fine. All right. So yeah, those are all the parts. I imagine there's a way to tell it to make it, to arrange it, or arrange all objects. I don't know what that means. Oh, yeah, I guess that works. All right, what's next? Slice the plate. All right, we're slicing. Warning, seems like has a floating region. Please reorientate. Lower leg simple. Of course it has. Wait, don't we? Oh, enable support generation. We have that off apparently. Advanced. Is that an advanced setting? Bridge. Very cool. Total time 3 hours. How do I enable? Of course I want support. Outside, process, global, objects, support, enable support. Alright, slice all again. Let's see. Quality, top quality, serious warning, conflict. Alright, separate the objects further apart. Well, didn't you do that? Spacing, increase spacing. Okay. Alright, that seems a little excessive, but preview. No, sorry. Slicing, arranging done, correct. Slice all. It's the first time I print on the bamboo, by the way, guys. Okay, that's a ton of support there. Ton support. Obviously, support is fine. It's just makes the surfaces rougher. I thought we could do that without support. Yeah, removing support also is not fun. Why do we need so much support? Wait, what does that part look like? Oh, I see. Yeah, where are we? Alright, I'm just gonna go with it. I have a bunch of filament actually. So I'm just gonna, I'm print all, PLA, printer. Wait, what do you mean? This doesn't support printing all plates. Oh, I used the wrong slicer. Oh yes, P1S. So we gotta slice again. Let's see if it gets any better. Print. What does printing all plates mean? What is a plate? Print. This appears to be working. Okay, so soon enough we should have a live stream of the printer printing. It's making sounds, you can hear it, that's good. My only question is if I have enough filament. And I guess there's only one way to find out. I think Bamboo actually tells you if you ran out of filament halfway through the print. Anyways, I'm probably gonna time lapse this part. I'm probably gonna time lapse this part. I'm gonna go heat up lunch. BRB. It's like watching TV. Can't tell if it's working. It actually has not started printing yet. It's doing like a bed flatness check. I can turn it off actually, but it just seems like a good idea. I'm gonna keep these running while I eat lunch, just so you can see like maybe like the first layer, and after that I'll just do like a little short video showing the final parts, and then on the next video, you know, and then I'm gonna source all the fasteners, and in the next video we can assemble, if that sounds good to you guys. And maybe some coding for the servos, just test the overall like envelope, and I'm sure there'll be some lessons to and revisions to make on the CAD. That's the first layer. Alright guys, I'm gonna pause the stream here. We're on layer 1 out of 343. It's gonna take 3 hours. I'll do a short video with the final parts in 3 hours from now. And next time we'll assemble this robot. So thanks a ton for watching. If that was entertaining, let me know. If I should change something, let me know. If I should talk less and just jump to when interesting things happen, let me know. But yeah, I'm excited to continue this project. So yeah, thanks again for watching.
A few moments later.
Alright, so it is now 3 hours later, and the parts have finished building here. You can see it in the camera. So we're gonna go take a look at that now. We can do some QA. We can maybe put in some thread inserts, and then the other thing is like while that was happening, I also remade the food here on Onshape. I couldn't figure out how to actually use the existing food. It kept giving me errors, so I just recreated one. And while I was recreating one, I actually found out there was an interference issue on the previous one. The through hole was too small. So like I said, always check these small details, always check the joints on the open source files. So I'm gonna go check those prints, and then I'm going to start printing the feet. All right, let's take a look. Yeah, looks good. It's really glued to the surface. The Bamboo has this like thing that pops right out. Actually, that wasn't extra or anything, it just came with the standard base model. Let's do. just doing some rapid QAing here. So first of all, you can see here that the holes that needed support, are actually going to be hard to. You need to go remove the support, but it's actually going to be a bit hard as it's completely flush there. You can barely see the outline of the hole. Of course, you can come from the other side, but it's going to have to be cleaned up. Same on these 4 holes here. You can also barely see it. On the other side, though, everything does look very clean. This is the first sprint I did with the bamboo, and so I'm running default settings, and it honestly looks pretty good. We have a 5.4 millimeter hole here, 3.3. I don't quite remember what that was. I think this was, so this is the upper, and so if the upper is here, and then this is the lower, and it fits in there somewhere, that would mean this is first of all, this is where the bearing sits. It's a very small bearing. I think we said it was like $30 or something. Now everything makes sense. Everything looks much smaller than in the screen. So this robot is pretty small. This is basically the full length of the leg, which is probably less than my arm. So I think that's a 4 millimeter hole. So this should be around like a 4.4 maybe, 4.2, perfect. The cam looks great. Again, I do regret all the support that was needed, but I do have to say these are all very clean looking parts. And so these, we said we were going to be putting hidden inserts there, so it should be 3.8. I think I'm gonna get in 3.6. And of course, these calipers are not the best tool to measure such a small hole. But I do have the thread inserts for these parts, so that's something that I could do right now. And then we have these push rods, which they're not buckling, so maybe that rib was actually necessary because they do feel very flimsy. These are 3 M3 holes, through holes, so it should be around 3.2. I'm getting 3 on the dot. And then same here, just a tiny version, 3 on the dot. But I think it will be fine. So I'm gonna go remove some support. I really don't like doing that. Well, it's actually, this one's popping right off. See, so I removed this support here, and then you can see here in this surface, you still have the ribs, so you gotta clean that up more. And so that's where the craftsmanship comes in. Let's try fitting some things through here. Let's see how that looks. 1 second. Without just checking CAD, I know this is where the servo is supposed to fit. So let's try and see if we can actually, if we're at least like within the vicinity. So you can see here, there's the 4 holes and then a big hole for the servo horn, and so these should fit right in there. And I can tell you it doesn't fit right in there. Let me clean that up a little bit. It is a very tight fit, if it fits at all. So I remove some support there. Again, if it doesn't fit, I wouldn't be too upset or surprised. Like I said, this has been my experience with things. So, it does fit. The holes do line up, and it is a nice fit. Only a little bit of play. We could tighten that a little bit more, and then you can see here the servo pops on this side. So, first fit is a win. Very nice. Yeah. Now we also have for the cam, we said we were gonna put some M3 threaded inserts, and so I have some M3s here. So this is what an M3 looks like. It's very small. Actually, every time I work with M3s, I say like this is gonna be the last time I work with M3s. And of course, as a through hole, it works great because it should be oversized. But now let's find a insert for that M3. And so, like I said, these are unlabeled. directly from AliExpress, and so I never know which ones are M3. So that one was an M3. So this is the thread insert. Everything is very, very small, and so we're gonna with an iron, with a hot iron, we're gonna come and we're gonna push this in there like that. And so you can already see that the chamfers we added, even though they're very small, they actually help in guiding this in. Then we're gonna clean this surface here. This is the fun one where somehow we're gonna put a bearing in there. And yeah, but so far pretty happy with the results. Yeah. What's next here is I guess ordering some bearings, and so so I'm gonna do that now, and they'll come in on Monday. So today's Friday, maybe Monday, maybe Tuesday, and so then we can finish the assembly on Monday, Tuesday, just depending on how the day job goes. But should have a working leg, you know, in a matter of a day or two. Definitely no more than a day of actual work on these. So so that's been cool. Yeah, thanks for spending an hour with me. And again, this is just the beginning. Obviously, eventually we're gonna have 4 legs to make an actual dog. And like I said, eventually we're gonna move away from these servos, and we're gonna have nicer kind of like those brush motor drives, like in the MIT Cheetah. So it should be fun, and maybe, who knows, in a year or two we actually make it to Antarctic. Maybe we make it to Mars. That's the dream.